record and then share screen. Let's see, this should be the first to start. Okay, so today we will start with a new topic, but not going to go too deep, okay, regarding deep learning also. And if you recall, last week we learned artificial neural network, is ANN, is it? Or you see multi-layer perceptron, is it? That's another name. And generally speaking, multi-layer perceptron, generally we have input layer, is it? And then we have hidden layer. And then we have output layer. So the goal is to what? Is to train model. Is it generally we use gradient, is it? Train model to find the optimize the weights. Is that true? That's the goal, is it optimize? So we have the feed forward, is it to from input layer all the way to output layer, is it with the data set, is it? And then you get the predicted, is it? This is predicted value, is that predicted value. And in ANN, how do we update the weights? So the strategy, who remembers the term? Update the weights. Who remembers the term?
Backlogging?
Yeah, very good, very good. You can send it to chat, okay, so that I can add bonus points, okay. Yeah, it's back propagation. Is it? Keep this in mind. So here from data set to predict its feed forward, is it? But to get the weight update, is it? We use back propagation, is it? We use that gradient. Gradient is regarding what? J over W, is it? What is this? So this is different weights, is it? What is J we call? Who still remember the name? So it's take the gradient. Is it? So the gradient concept is to take what? Partial derivative regarding weight. This is what? This is called loss function. Okay, so we need to remember this name. Okay, loss or cost function, is it? Because if you said, okay, you know neural network, this basic terms we needed to know, okay. And the goal is try to minimize, is it, the loss function, is it? And so we take a gradient. But if you take gradient because of multi-layer, is it? And then it's going to be regarding some intermediate variables, is it? So then you need, it involves the multiplication of huge matrix, is it? So not efficient, is it? So that's why we use back propagation. Is it? Back propagation is regarding the arrow. Is it calculate arrow, and arrow propagate back to previous layer. Is it? Using arrow. So we are not going to directly do the gradient calculation, is that we use arrow to proxy back, is that to find the optimized weight updates. Okay, so anyway, so that's the general concept regarding ANN. So just a quick review, okay. And so over here, there is a concept called, we always hear this buzzword, is a deep learning, is it? Deep learning be based on what? It's based on neural network, okay? Based on neural network, and it's multi-layer, not a single layer, okay? Multi-layer neural network. And generally speaking, you at least need to have one hidden layer. Okay, that's what we call deep learning, is it? And the deep learning is especially good for large data. Because with large data, the traditional machine learning algorithm model that we learned before, is we learned quite a number of algorithms, is it? Their performance. So if we draw something, so this is data size, is it? This is performance. Performance, is it? So regarding that, then generally speaking, it's maybe looks something like this, is it? But if we have, if we use a deep learning, so this is traditional, is it? But if you use deep learning, then it, you see the difference. So this is deep learning. So the performance can be improved quite a lot. Okay, so that's the concept. That's the benefit of deep learning. Okay, so the more data, the better. Is it with regarding deep learning compared with traditional learning? And also another advantage, especially if we CNN, we will see today. Okay, so the deep learning, basically, like over here, the concept is it's working like with hierarchical feature learning. Hierarchical feature learning. Okay, so that's also one of its a characteristic with deep learning. Okay, so hierarchical. And we already mentioned back propagation. Okay, back propagation. That's the strategy to update the weights, is that using gradient. We didn't directly use gradient to do the calculation. And over here today, what we will learn is CNN, because you may see this a lot in deep learning. ANN, it's artificial neural network. Okay, you may also see DNN. This is deep neural network. We also see, today we will learn CNN. CNN is convolutional, okay, neural network. So it's still based on neural network, but here we have a word called convolutional. Okay, so what that is, we will see that. You may also see that RNN, and I don't think we will have time to learn that. Okay, but I will see if I will do some record a video, okay, short video and post on our website maybe. So this is recurrent neural network, RNN, okay. And CNN, we will see today, it's especially good for image. Okay, recognition, okay, because images, previously when we see that MNIST, that you already see its features, too many features. Is it because it's based on how many pixels? Is it that's 28 by 28, it's already 784 features. Is it? And in the applications, you have high definition photos, is it? Then there are more. So the pixel size is much more bigger than this, is it? So there are more features. And how do we deal with that? So how can you catch the most important feature in image? is that we will see CNN is quite helpful. Okay, so the word is called convolution. Okay, so CNN says its main function is extract salient. Salient is the most relevant feature. Okay, relevant feature. Okay, and we generally here it's also a neural network can be served as a feature extraction engine. Okay, engine. Especially we will see with deep convolution neural network. Okay, so it's called the feature hierarchy. Okay, by combining it as a low-level feature in a layer-wise fashion. So here we will also see what is the layer-wise fashion, and previously when we discuss our data set, it's always 2D, is it? So you have samples. So samples is rows, is it? And then you have features, is it? That's column. Okay, but today we will see the data is going to be in 3-dimensional. Okay, how that works. Okay, so let's see. Okay, so that's the general idea about, so just some introduction about CNN. Okay, so here it says CNN usually perform very well for image-related tasks. Okay, and due to 2 important ideas, it's sparsely connected. This is especially for image. Okay, because the pixels may be in this corner has nothing to do with the other corner, etc. So that's why we say it's sparse connectivity regarding image. Because of this feature, that's why you will see CNN is quite efficient. Okay, and also it says parameter sharing because the same weights it says can be used for different patches of the input image. Okay, so because of this, then CNN is quite useful. And I think whoever invented this, CNN is quite intuitive. Okay, so the father of CNN is the founder basically, and it's Yan LeCun. Okay, so this is CNN. Okay, CNN. And RNN, especially with the LSTM, okay, long short-term memory, etc. That's RNN. Okay, the name for this for the founder is Jürgen Schmidt Huber. Yeah. So if you read the theory, you will find amazing. Okay, the ideas. Okay, CNN. So CNN, let's see the its structure. Okay, it says composed of, because anyway it's artificial, it's neural network. Is it neural network? The basic idea is the layers. Is it multiple layers? Multiple layers, is it? But here the idea is when you add the layers, you are not just randomly add some layers, add some neurons, is it? So you will make the specific layer serve for some purpose and can filter out, can extract some features for you. Okay, so that's the idea. So that's why over here it's CNN, it's composed of several. First is called convolution layers, conv layers. Okay, and after that, generally it also, but it's multi rounds of this, subsampling, okay, called pooling layers. Okay, pooling layers. So you will see this a lot, convert and then followed by pooling. Okay, and it's one round, and then you can repeat this, convert plus pooling. Okay, so that's it. And then after that, we also need to flatten it. We call it fully collected layer, so FC. So maybe after this, you will have FC. FC means fully connected layers. Okay, fully connected layer. Fully connected layers generally says just our multi-layer perceptron. Okay, but this two layer, it's not going to be 2D. Okay, it's 3D. Okay, this is 2D. Okay. Okay, so here it says for the fully connected, then every input unit is connected to every output with weight. Okay, with weight. So that's the general composition of CNN. Okay, so then let's take a look. What is called convolution? Okay, convolution. So some basic idea. So suppose you have a 6x6 image, the pixels, and you have the pixel values is between 0 to 255. That's what we previously learned, is it? And here with convolution, the concept, you need to select a filter, or we call it a kernel later on when we learn it in TensorFlow, okay? So you need to pick a filter, okay? The filter is going to be same dimension as its input, okay, as its input. Okay, so here suppose our filter is some 3x3 matrix. Okay, so this is, if you take a look, you will find the first column is all 1, the third column is all -1, and the middle one is 0. So you have some specialized filter kernels. Okay, and then what you are going to do is you are going to apply this filter to the first 3x3 cell, okay, on the image. Okay, so like over in this diagram shows, is it? So you can put the corresponding value on the original image. What it's going to do is it's going to multiply all of the corresponding values. Okay, and then sum them together, you find this -5, is it? Then you put this -5 to a new matrix at this cell. It's -5. Is it? It's -5. Okay, so that's regarding this. Is it? Because this is a filter, and then I'm going. So assuming here the stride is 1. So that means each time I'm going to use this filter. So this is the first time I filter it like this. And then the second time, I'm going to move this filter to the next 3x3 cell. Okay, so you move the filter, is it by 1 cell? Is it by 1 cell? So then you're going to do the same thing, 1, 1, 1, and the -1, -1, -1. So multiply each cells and sum them together, you will find -4. So you put it in this matrix. Okay, and then you move on to the next one. So because the stride is 1, is it? So you just advance the field. So it's kind of like, you know, you use some magnifiers that you keep moving. Like, so we can also call this sliding window. Is this assuming like you have some window, then you slide, is it? Yeah, so then you get to the next, you will find this value, is it? So keep doing, is it? And then what the next one is going to be the last one, is it? The last one, then you get there. And then you can move down, is it? Same thing, you move down. So you finish the horizontal, then you go to vertical. Is it moving down? So then you come up with this new matrix, is it? So this is called convolution, okay, convolution. And then you may ask, what this serves for, okay, we will see that. Okay, but the idea over here, if you recall that previously, okay, let's go back to the previous slides. Oh, go to the previous slide. And if you record this, it looks like, you know, the middle parts, is it the middle parts? Your filter can cover it a couple of times. Is it like those corners? Is it they just covered once? So basically just covered once. Is it when you do this calculation, it's just this 3 just use once. Is it or twice? Is it just once in this case? So it's kind of you didn't give the cells equal importance. Is it equal opportunity? So in order to avoid this kind of issue, what we apply a technique is you can do padding. Okay, you can do padding. So padding, so this is the original. Is it? This is original. And then you expand it with all zeros. Okay, with all zeros. So those are called padding, okay, over here. So this padding with, so you enlarge your original input matrix. Okay, so that's technique, it's called paddings. Okay, then next move to the next one. Okay, so here it shows we apply the paddings, is it? And then you can come with some new results. Okay, then next let's see another concept so-called convolution over volume. Okay, volume. So in convol it's 3D, is it? So even though the image is 2D, is it? But generally speaking, image is 3D, is it? This is regarding the pixel, is it? But there is a third one, we call it color channel. Okay, there is some channel regarding, okay, the color channel, generally speaking, for image, is it? So if that's the case, then how do we apply the convolution? Is it convolution? So in this case, you see, here it shows 3 channels. The 2D parts, it's all the same, is it? So this part is the same, but you repeat 3 times, is it? And each time with some different channel, is a different channel. Then in this case, your filter also, you also need to have the 3D channel, okay, 3D filter. So your filter, because filter needs to be the same dimension, is it, as the input image. So your filter then also needed to be 3. It also need to have 3 channels, is it? But be careful here, okay, after you convoluted, is it? It's go from 3D to 2D. Okay, so be careful to 2D. So what it does is the first layer of filter deal with the red one. The second layer deal with the green one. And the third layer deal with the blue layer, is it? And after that, you sum of all 3 layers together. And then you fill it to that single cell, okay? So that's how this works. Okay, so we understand how convolution over volume, is it? And later on, we will also see, okay, for the same input image here, you can apply different filter. So this is filter 1. And here we have filter 2. Okay, you can apply different filter. And then after this, is it? So the input image is 6 by 6 by 3. The first filter is 3 by 3 by 3. The second is also 3 by 3. Okay, both are 3-dimensional, is it? So for the first one, you will have a convoluted result. For the second filter, you also have a convoluted result. Okay, so then your output in this case is going to be 4 by 4 by 2. Okay, so the output is going to have 2 layers. So see how magic this is, okay? Because later on we will see this is, so the convolution regarding the dimension change is very, very useful. Okay, how do you change? Okay, so you can apply different filter. Okay, because each filter can serve its purpose, serve some sole purpose, is it? And then the first filter can serve its purpose, the second filter can serve its purpose, is it? So we can say, okay, first filter, we say, okay, let it detect all vertical edges. And then the second one, we can let it detect all horizontal edges, okay, regarding image. So let them to get different edges in a graph, okay, in an image. Okay, so let's see what that idea is. You may say, oh, what is that? So let's take a look at this picture. Is it? So this is an image. Is that image? So clearly you have some horizontal line. Is it horizontal line? And we also have some vertical line. Is a vertical line. So you see the horizontal filter. So if you want to kind of get out of all of the horizontal features, the edges, is it? Then you can apply the filter looks like this. And if you want to get off the vertical line, then you apply this vertical filter. So then if you apply vertical, you will get this. And for the horizontal, okay, so I should reverse. Is it if you apply horizontal filter, you will get the output looks like this. Here you will get output like this. So it will extract, is it detect the corresponding feature you want to detect in this image. Is it? So this is very useful. Is it? That's why we see CNN is amazing. Is it? Okay, and then next, let's see. Okay, so the idea. So over here, is it you have the 3D image, not 3D, the 3-dimension input, is it? So we have 3 channels. So the input is 3 channels image, is it? And over here, be careful, okay? So we have 5 filters here. So here, for that single image, you apply 5 filters. Then maybe you said, okay, I want to detect some horizontal edges, some vertical edges, some diagonal edges, or some specific spot. Is there something like that? Then you can have 5 filters. Is there 5 filters? So after you apply the 5 filter, what the output is in this convolution layer, then you will have some 2D, is it? Some suppose we call it A by B, is it? And then by 5. So the last dimension, the third dimension, depends on the number of filters, okay? And also be careful, okay, for each of the filter, is it? So you see the filter dimension, is it the third one, got to be the same as the input, as its input. Okay, so this must be the same. So you see your filter need to be exact same dimension, is it the third dimension, the number of channels, okay, channel. And then you will have 5 layers. Is that 5 layer? And we can later on also doing pooling, okay, because this image is still quite big. And if you just want to get the most important pixels, is it from the filtered out result? Is it, how do we do that? Or doing the average, is it? So how do we do that? That's we will see later. Okay, then let's see how this related with our neural network. Is it neural network? And here it says, once we get output after we convolving over entire image using a filter, is that we can add a bias term to the outputs, is it? And then apply an activation function to generate activations. I said this is called one layer of convolution network. Okay, convolution network. And if you recall previously for neural network, this is net input. Is it net input is always the previous layer's activation times the weight. The weight is what we train, is it? And the bias is also what we train, is it? And then you apply the activation function. Is it? And then you can get output for the current layer. Is it? And here it says, okay, what is A regarding here, or X, is it? Is our input image. And the filter is the weights. Okay, filter is the weights, okay. And then you just apply some activation function. That's what a convolutional neural network works, okay. So the weights here, is it? The weights here comes from what? From filter, okay, from filter. So this is a little bit different from previously what we learned, the neural network, is it? So here you apply the weight, you provide the weights, is it? And here your weights' purpose is to get, we call it a salient feature. Is it just like in that image, you want to get horizontal or vertical edge, is it? Okay, so that's the idea about the weight, okay, and the input. Okay, then let's see. Here it shows as a typical convolution network, what it looks like, is it? So this is input image, 39 by 39 by 3. You have 3 channels, is it? And the filter size is also 3. Okay, it's also 3. And this is a stride. Stride is 1, so that means each time you just advance by 1 column or 1 row, is it? And how many filter you apply? You apply 10 filters, is it? That's why the output you have is 37 by 7, but it's by 10. The third dimension is 10, so the depth is 10 layers. Is it 10 layers? And then you can apply more, is it? So you can continue doing this, is it? Continue doing. So the next one is 20 filter, and this is the filter size, is it? After that, under the stride, you see, if you change the stride, and this size got also decreased a lot, but it's with 20 layers, is it? And you can keep a convert, is it? And then you get, you see in this case, your dimension kind of increase from 3 to 40 layers for the last convoluted layer, is it? And then after that, over here, we are going to do neural network part. Neural network part, is it? So we need to flatten it. Flatten from 3D to what? To just the corresponding input, is it? And then you apply activation sigmoid or softmax, is it? Then you can find the output, the calculated output. So this is a typical one, okay? So typical, generally speaking, convolution network has 3 types of layer: conv layer, pooling layer, and the fully connected layer. Okay, so keep that in mind. And what is pooling layer? That we just talk about, but we never mention. Is it? So suppose this is after conv, is it? After convert, then you get this, is it? But it's still 4x4 matrix, is it? And here we say if you apply maximum pooling is based on what matrix you are going to apply, is it? So here suppose, okay, I want to have 2x2, is it? So then in this green cell, you just find the maximum number 9. And in this one, it's 2, is it? This one is 6. Here you have 3. So for each patch, is it? For each patch, you find the maximum value, is it? And then you get a new output. And clearly you can see the dimension size decrease, is it? From 4x4 to 2x2, is it? So your image size got decreased, okay? So that's called a pooling layer. So generally speaking for CNN is you have the original image, then you apply, okay, first convolution and pooling, and for the result, then you can apply second time of conv and pooling, is it? And then you do flatten, is it? And multi-layer, so hidden layer. So over here, this is kind of like input layer, hidden layer, and output layer, is it? And finally, you apply the softmax, is it? Sigmoid, is it? To find the predicted result, is it? So that's multi-layer. And here once again, okay, so repeat. Okay, so that's the general idea about CNN. We kind of understand it. So next, let's take a quick look of the coding part, okay? And if you recall that MNIST one, is it? MNIST. And MNIST one, when we use TensorFlow ANN, is it? And remember, okay, with TensorFlow high level, so it's TensorFlow high level API, is it? The low level one, it's quite complicated, is it? Because you kind of need to start from scratch, build the neural network. But with the high level API, the Keras one, it's very easy, is it? Simple. So you just use, generally we use a sequential model, okay? There is another one called functional model. Okay, if you are interested, you can investigate it, okay? But here for sequential is you just add layer by layer, is it? So the first time, of course, we need to flatten, is it? 2784, is it? The input. Okay, and then you provide the first layer. So this is input layer. Is it input layer? Okay, input layer, you need to pick the activation, is it? And we said, okay, we apply that rectified, is it? Linear unit. Linear unit Is it we apply that strategy? Is it we didn't apply? You remember we said we don't use sigmoid. Is it no sigmoid? Okay, because there are some disadvantages with neural network if you use sigmoid. This rectified linear unit is quite efficient. Okay, and then drop off. We will discuss that tomorrow. Okay, and after that, is it here we have output layer. We don't have any hidden layer in this case. Is it the activation to pick the softmax? Is it softmax generally is for the output layer, okay? Because that's give you the possibility. It's not just 1, 0, is it? It's the possibility it's being certain value, is it? That's what softmax mean, okay? So keep that in mind, okay? These two are quite used a lot, okay, in neural network. And after that, is that you remember, then you need to compile the model. When you compile, you need to provide what the solver is, or we call it optimizer. Is that what the loss function you're going to use, and the performance matrix. Is it? So here it uses Adam. Adam is stochastic. Is it does batch? Is it and online? And the loss generally we can apply certain cross entropy. As here it says we apply sparse categorical. As you can also select a binary sparse category and sparse categorical cross entropy generally for multi-class classification or MSE. Okay. Later on we will also see. So it's mean square error. Okay, for a regression. Okay, so if you want to do regression, you need to choose MSE. Anyway, so that's the and then we can fit the model, is it? And then we can evaluate the result, is it? And we also mentioned the verbose and epoch, is it how many times you want it to train, is it? And verbose is if you wanted to see this progressing bar, is it? Okay, so that's the we discussed last class. And over here, we are going to use convolution. So pretty similar, okay. So you still use sequential, then dense convolution and maximum pool D. So convol layer, pooling layer, and of course, we also add the dropout layer, is it? Okay, so still for the MNIST, okay, nothing different. You load the data, you do train and the testing, and then you need to shape data. But this is one important thing, okay? You need to normalize data, okay, for all neural network, okay? You need to either normalize or standardize. Okay, so don't forget about this step. It will impact your calculation result a lot. And here we have 3, is it? So we have, oh, here it just shows the dimensions, okay. And then let's see, how do we apply convolution? So we use a sequential model, is it? So input is 28 by 28 by 1. Be careful, for convolution, you need to reshape. Your input is 2D, is 28 by 20. But for convolution, if you want to apply, you need to first reshape it 28, 28 by 1 to 3 dimension, okay? And then we apply, here we set the kernel size. So you add, okay, you can add the first layer is convert to D. Is it? The first parameter 32 means how many filters. So here, you're going to have 32 filters, okay? So maybe 1 for horizontal edge, 1 for vertical, 1 for diagonal, and some other different things, is it? So you apply 32 filters. And each filter size is 3 by 3 by 1, is it? By 1. And the activation, what you're going to apply, is it? We apply rectify linear unit, is it? And the kernel initial is Hey uniform. And you also specify the original input shape, is it? And after that, did you see you add the pooling layer, Is it a pooling layer? And after that, we flatten. Is it we flatten? So flatten, after you flatten, you convert it from 3D to 1D basically. Okay, not one dimension, two-dimensional, is it? But it's just one column. Okay, and then you apply the neurons. Here you provide the number of neurons, is it? For the output layer, is it? And what kind of activation, is it? And oh, this is just the first output, not the output layer, the hidden layer, we can call this. Okay, this is a hidden layer, and then we have this output layer, soft max. So you can see it's also pretty straightforward. Okay, so you just add a convolution layer, pooling layer, and then you flatten it. Then after that, so after flatten, then you provide some dense layer. Okay, as regarding the drop off later on, we will discuss. Okay, and that's it. Is it? So then you can have the, then after that, that's just model. Is it? After the model, we still need to do the compile. Compile, then same thing, you need to provide optimizer. So similar, is it, as a neural network. And the loss function is that here because it's multi-class classification, you select sparse categorical cross entropy. And then you can do fit, and then you can collect the accuracy. You can also use it to predict image. Okay, so this is the general idea about CN